बिस्मिल्लाहिर्रहमानिर्रहीम अल्लाहुम्मा सल्लि अला मुहम्मदिन व अला आलि मुहम्मदिन व बारिक व सल्लिम। रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़्दतम मिन लिसानी यफ़क़हू क़ौली। Assalamu alaikum. I am Dr. Umar Farooq, Divisional Public School and Intermediate College, Lahore. As you know, we are studying matrices, Chapter 1, Class 9. Today's topic is types of matrices. In your textbook, 12 different types of matrices have been discussed. That is, row matrix, column matrix, rectangular matrix, square matrix, null matrix, transpose of a matrix, negative of a matrix, symmetric matrix, skew symmetric matrix, diagonal matrix, scalar matrix, and identity matrix. In today's lecture, we'll study them in detail. So, first of all, row and column matrices. A matrix is called a row matrix if it has only one row. On the other hand, a matrix is called a column matrix if it has only one column. For example, matrix M is a row matrix of order 1 by 2, and matrix N is a row matrix of order 1 by 3, that is 1 row and 3 columns. On the other side, matrix P and matrix Q are column matrices of order 2 by 1 and 3 by 1 respectively. Next we have rectangular and square matrices. A matrix is called rectangular if its number of rows is not equal to the number of columns. That is, M is not equal to N. Conversely, a matrix is called a square matrix if its number of rows is equal to the number of its columns. That is, M is equal to N. As in a rectangle, the length is different from width, while in a square they are equal. That's why a rectangular matrix looks like a rectangle while a square matrix looks like a square. For example, matrix A has 3 rows and 2 columns. Matrix B has 2 rows and 3 columns. Matrix C has 1 row and 3 columns. And the order of matrix D is 3 by 1. So, A, B, C, and D are all rectangular matrices, as in each matrix number of rows is not equal to the number of columns, whereas matrices E, F, and G are all square matrices, as in each matrix number of rows is equal to the number of columns. Number 5 is null matrix, also called zero matrix. A matrix is called null or zero matrix if each of its entries is 0. For example, here we have null matrices of various orders. Note that a null matrix is represented by the letter O. At number 6, we have transpose of a matrix. Transpose of a matrix is obtained by interchanging its rows and columns. For example, this is matrix A and this is its transpose. Did you see what happened? Let me display it again. Now, concentrate and note the interchanging of rows and columns. This is first row of matrix A, 1, 2, 3, which becomes first column in its transpose. Similarly, second row becomes second column, and third row becomes third column. So, this is matrix A, and this is its transpose. Note that the order of both A and A transpose is same because A is a square matrix. Now consider matrix B. First row becomes first column in the transpose of B. Second row of B becomes second column in its transpose. So order of B is 2 by 3 while that of B transpose is 3 by 2. Matrix C is a row matrix which becomes a column matrix after taking its transpose. Note that the transpose of a matrix is denoted by putting small t in the superscript of the symbol of the matrix. Number 7 is negative of a matrix, which is obtained by changing the signs of all of its entries. Consider, for instance, matrix A. If I rewrite this matrix by putting minus signs with 2, 3, 4 and 1 and removing the minus sign of 6, I get negative of A. Negative of a matrix is denoted by putting a minus sign with its symbol. At number 8 we have symmetric matrix and number 9 is skew symmetric matrix. A square matrix is said to be symmetric if it is equal to its transpose. That is, a matrix A is symmetric if A transpose is equal to A. On the other hand, a square matrix is said to be skew symmetric if its transpose is equal to its negative matrix. That is, a matrix A is skew symmetric if A transpose is equal to negative of A. Consider, for example, this matrix M. To check whether it is symmetric or not, we find its transpose and we get the same matrix M. So, matrix M is symmetric as M transpose is equal to M. Consider another matrix A. This is its transpose, which is of course different from A. So, matrix A is not a symmetric matrix. Now look at this matrix B. Its transpose is not equal to B. So B is not symmetric at least. If we rewrite its positive entries as negative and then take minus sign common, we get negative of B. This implies that matrix B is skew symmetric matrix. The last three properties of matrices are very important, which are diagonal matrix, scalar matrix, and identity matrix. A square matrix is called a diagonal matrix if at least one of the entries of its diagonal is non-zero, while all the other entries are zeros. Similarly, a diagonal matrix is called a scalar matrix if all the diagonal entries are same and non-zeros, while a diagonal matrix is called identity or unit matrix if all the diagonal entries are 1. So, a diagonal matrix may be of two types, that is, scalar matrix and identity matrix. Note this: a scalar and identity matrix is a diagonal matrix, but a diagonal matrix is not a scalar or identity matrix always. Let's have some examples of these types. Look at these matrices. and concentrate on the diagonals. By the way, all of these matrices are diagonal matrices, but I have divided them into three categories. Let's start with identity matrix, which is denoted by I. Note that there is no diagonal entry except one. So, an identity matrix is defined as a diagonal matrix such that all of its diagonal entries are 1. Now consider some scalar matrices K, L, M and N. There is no dissimilar element on the diagonal in each matrix. So a scalar matrix is defined as a diagonal matrix such that all of its diagonal entries are same and none of them is either 1 or 0. But the matrices A, B, C, D and E cannot be called as identity or scalar matrices, although they are diagonal matrices. It means that every scalar and identity matrix is a diagonal matrix, but every diagonal matrix is not a scalar or identity matrix. So a diagonal matrix is defined as a square matrix if at least one of the entries of its diagonal is non-zero, while all the other entries are zeros. Now it's time to solve exercise 1.2, whose question number 1 is, from the following matrices identify row, column, unit and null matrices. Recall that a row matrix consists of only one row. So the matrix B is the row matrix. A column matrix consists of only one column. So there are two column matrices, matrix C and F. A unit matrix has diagonal entries 1, rest are zeros. So we find only matrix D as a unit matrix. While a null matrix is that whose each entry is 0. So there are two null matrices, that is A and E. Question number 2 is, from the following matrices identify square, rectangular, row, column, identity and null matrices. Recall that in a square matrix M is equal to N, and in a rectangular matrix M is different from N. So there are three such matrices, matrix 3, 4 and 8, in which M is equal to N. So 3, 4 and 8 are square matrices, while the rest of the matrices are rectangular matrices. That is matrix number 1, number 2, number 5, number 6, number 7 and number 9. They are rectangular matrices. A row matrix consists of only one row, so matrix number 6 is a row matrix. A column matrix consists of only one column, so matrix number 2 and 7 are both column matrices. Identity matrix is matrix number 4. Null matrix is matrix number 9. Next question, from the following matrices identify diagonal, scalar and unit or identity matrices from A to E. Let us first simplify matrix E and then recall a diagonal matrix has at least one non-zero entry of its diagonal. The rest are zeros. So in this way, each of these matrices is a diagonal matrix. A scalar matrix has all the diagonal entries same and non-zero. Rest are zeros. So matrix A and matrix E both are scalar matrices, while an identity or unit matrix has all the diagonal entries 1 and rest are zeros. So we have only matrix C as an identity matrix. In the next question, we have to find negative of matrices A to E. Recall that negative of a matrix is obtained by changing the signs of all of its entries. In this way, this is negative of A, this is negative of B, negative of C, negative of D, and this is the negative matrix of matrix E. Note that every positive entry has become negative and every negative entry has become positive in the negatives of all of these matrices. In question number 5, we have to find transpose of matrices A to F. Recall that the transpose of a matrix is obtained by interchanging its rows and columns. In this way, transpose of a column matrix A is a row matrix, and vice versa for matrix B, that is, transpose of a row matrix is a column matrix. This is C transpose. C is of order 3 by 2 and its transpose is of order 2 by 3. This is transpose of D, this is transpose of E, and this is transpose of F. Note that every row has become column and every column has become row in each of the transposes of the given matrices. In the last question, we are given two matrices A and B and have to verify that transpose of A transpose is equal to A, and number 2, transpose of B transpose is equal to B. Let's verify them parallelly. These are matrices A and B. We find their transposes. Now, taking transpose of both sides again, we write it like this. Put a small t in the superscript and find the transpose. This is the transpose of A transpose, and we compare it with matrix A. They are same. On the other hand, transpose of B transpose is equal to B. Hence proved that the given statements are true. If you have any questions, please do write in the comments below. Thank you.